Sample problem 18.4 is another qualitative aspect of acid-base chemistry that has to do with identifying conjugate acid-base pairs. So again, if we look at our summary sheet here, we can see that conjugate acid-base pairs are species related by plus or minus a hydrogen ion. And so there's kind of three flavors that you can get for this problem. You're going to get the flavor kind of that we have here, where you're given an entire reaction. And so it's easy to kind of see who's related by plus or minus a proton. So hopefully you can kind of look at this species and see that they're related. So let me just rewrite this one here. H2PO4 plus CO3 2 minus, HCO3 minus, plus HPO4 2 minus. So kind of the easiest flavor of this problem is you're given a chemical equation and you need to just find who's related by plus or minus a proton. So hopefully everybody can see that these guys are related and these guys are related. So you always are going to write something as an acid and something as a base on the left-hand side of the equation, on the reagent side. So this guy lost a proton, which must mean that this guy is the acid, and so we call this guy over here the conjugate base. If this guy is an acid, that must mean that this guy is behaving as a base. And if he's behaving as a base, that means he's going to take a proton, gain a hydrogen atom, and gain a positive charge, and become a conjugate acid. So kind of the easiest flavor is where you're given an equation, and you just basically need to identify the species that we have there. Let's just kind of go through problem B here, because this is the same kind of a problem where you're given the whole equation and you just have to identify and match up who's who. So again, seeing a relationship here and a relationship here. This guy picks up a proton, which means that this guy must be behaving as a base and generating a conjugate acid. I did this one first because water is one of those species that water can behave actually as an acid or a base. If we look here, we can see that it's behaving as an acid because it generates hydroxide, which is the conjugate base of this acid. But I started with something where it was easy to kind of see what happened. This guy had to be a base. It actually had no hydrogens it could get rid of. Again, water could be behaving as an acid and generating hydroxide, or could behave as a base and generate hydronium. So we've answered and kind of gone through this problem already, but I want to tell you about a couple of different ways you can think about this kind of a sample problem. So let's just call this other ways to think about conjugate acids and conjugate bases. So kind of a second flavor, so this is kind of the easiest. The second flavor is I might give you just what I'll call a single species. So you might be given a single species. And then I'll just ask you, who's the conjugate base of this? Or who's the conjugate acid? So just kind of picking up from this problem, I might write this molecule, this ion, and say, tell me who the conjugate acid of this is. And you need to write this species. If I gave you water and I asked you to write the conjugate base, you'd tell me hydroxide. But I could also ask you, who's the conjugate acid of water, which means you'd write H3O+. So other kind of flavors of this problem are where you kind of are given single species and you're asked to think about who the conjugate acid or conjugate base is. Kind of the third flavor, which is the hardest, is maybe you're only given reactants for an equation. Okay? And so in this case, you need to determine who is going to be the acid or the base. So let's imagine this problem that we had here. If all I gave you were these two species in solution, well, we already talked about this guy can't behave as an acid. It doesn't have a hydrogen to give up. So in this case, we know that this guy is going to generate a conjugate acid and water will generate a conjugate base. So sometimes it's relatively easy to figure out just by looking at the species that are there. And as we'll see later on when we talk about salt solutions, sometimes you might need to consider the acid or base potential of these different species and ask who is likely to be the acid and who is likely to be the base. So sometimes, again, this is going to be easy if there's only one option. So for example, SO3 2- can only act as a base. Or you might have something like water, right, that has the ability to do both. But if this guy is going to be a base, water must be an acid in this chemistry. And thinking about this kind of chemistry is going to become important as we deal with salt solutions later. Just as a little bit of a heads up, if you, for example, had a sodium sulfite solution here, SO3 again being sulfite, if you had a sodium sulfite solution that you dissolved in water, you would actually generate hydroxide ions in solution, which means that that solution would actually be basic. It would have a pH greater than 7. So don't worry if that's a little bit confusing right now, a lot more than is related to this specific problem, but we will get to that stuff towards the end of this chapter.